Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss the resolving power of telescope. Let's begin. What is telescope? Telescope basically used to see the distant objects. If there are two distant objects at infinity that can be easily seen with the help of telescope. There are some technical terms related to telescope. On the basis of these technical terms, we can analyze what type of telescope it is. First one, the limit of resolution. What is the limit of resolution? That is the smallest angle subtended by the two distant objects which can be just resolved at the objective of telescope. If there are two distant objects, that be the telescope here, objective of that of given telescope. So, the minimum angle subtended between these two objects at the telescope, that angle, the minimum angle, let that angle be the theta, which is known as the limit of resolution. The smallest angle subtended by the two distant objects which can be just resolved. We can just resolve these two distant objects at the objective of that of telescope is known as the limit of resolution. That is the limit of resolution of the telescope. Next, resolving power of telescope, that is the reciprocal of limit of resolution is called the resolving power of the telescope. The reciprocal of the limit of resolution is known as the resolving power of telescope. How the telescope easily distinguish these two objects when these two objects are at infinity. Next, Rayleigh's criterion. In case of telescope, there are Fraunhofer diffractions takes place as the objects is at infinity. So, what be the conditions? These two objects can be easily distinguished, or we can say these two objects can be easily resolved by the help of the telescope. It must satisfy the Rayleigh's criterion. What is that Rayleigh's criterion? The two objects will be just resolved if the central maximum of one object coincides with the first minimum of the other object and vice versa. Let me understand. There are two objects at infinity. So, due to first object, let the diffraction pattern we see maxima, minima and so on. This is the central maxima, that be the first secondary minima. Due to another object, let the diffraction pattern central maxima, minima, maxima and so on. If the central maxima of one coincides with the first minima of other, that is the central maxima of one is coincides the first minima of other, then we can say we can easily distinguish the two objects when these two objects are at infinity. That will be the Rayleigh's criterion. Let me mathematically show what exactly happened in case of telescope. Let me consider a telescope, objective of the telescope AB and the objective of that of telescope of diameter capital D. D be the diameter of objective of telescope. That is also a circular aperture. As the objects are at infinity, here we have the Fraunhofer type of diffraction. Let there will be a screen which is at a distance of the focal length of that particular objective of that telescope, and that screen is placed at the focal plane of that of lens. The focal length be small f. Let a object is O. Due to that object, the rays are coming, parallel rays, and the object is at infinity. These rays are focused at point P. Due to these rays, here we have interference pattern, just like alternate dark and bright fringes. Next, another object O dash, which is just at infinity. Due to that object, that be the angle, let d theta, which is basically known as the limit of resolution, means the smallest angle subtended by the two objects which can be just resolved, that is the limit of resolution d theta. So, after that the ray here also angle d theta, angle d theta at point P dash, we again achieve a diffraction pattern like this. These are the intensity distribution. According to Rayleigh's criterion, the central bright of 1 is coincide with the first minimum, and the distance, that be the minimum distance in between these two. That is why we can easily distinguish the two objects. Now, we mathematically show here the path reference between these two rays, draw a perpendicular here, here is Bn, that angle subtension is equal to d theta. So, the path reference is equal to, that be the diameter d, that angle is equal to d theta. According to the sin d theta, we have Bn divided by AB. So, Bn, that is the path difference, is equal to AB sin theta, which is d sin d theta. From right angled triangle ABN, sin d theta is equal to Bn divided by AB. or path difference Bn is equal to FB sin d theta, or Bn FB is equal to the diameter of that of telescope d sin d theta. Since d theta is very small angle, therefore sin of d theta is nearly equal to d theta. Here we have the path difference Bn, is equal to d into d theta. If the path difference is lambda for what? For fast minimum. We have the path difference is integral multiple of lambda. For fast n is equal to 1, so path difference is equal to lambda, then the fast minimum of p dash falls on the central maximum of p. So I write it, if path difference is lambda, look at that of expression, if the path difference is integral multiple of n lambda, that is the condition for minimum. For fast minimum n is equal to 1, so path difference is equal to lambda, that be the minimum. Here if the path difference is lambda, then that be the fast minimum. The fast minimum of p dash falls on the central maxima of p. That minimum falls on the central maxima of p. Therefore according to Rayleigh's criterion, will be fulfilled, and object O and O dash will be just resolved. Object O and O dash will be just resolved. Therefore path difference is equal to lambda. For first minimum condition, so path difference is equal to d theta. d theta is equal to lambda, or d theta is equal to lambda by d. What is d theta? D theta is the limit of resolution according to our definition. So limit of resolution, or limit of resolution d theta is equal to lambda by d. But actually experimentally we saw from Ayres formulation R is formulation that d theta is just increase the value 1.22 lambda by d. Next, that is the limit of resolution. Reciprocal of limit of resolution is termed as the resolving power. So, the resolving power, therefore, resolving power is equal to 1 by d theta, reciprocal of limit of resolution, which is equal to d divided by 1.22 into lambda. So, the resolving power is equal to d divided by 1.22 by lambda. From that of expression, the resolving power is depend upon the diameter of that of telescope. If the diameter of that of telescope is large, so the resolving power will be maximum. And again, the wavelength of the source of light, if the wavelength is large, again the resolving power will be minimum. From that of expression, it is clear that the resolving power depends upon the diameter of telescope, diameter of objective d, and wavelength of light, which is lambda. Therefore, for greater resolution, objective of telescope have larger aperture. For greater resolution, the objective of telescope to have large aperture, that will be the diameter. For greater resolution, the objective of telescope to have large aperture. If the radius of central bright disk, since the aperture is a circular aperture, the diffraction pattern is just like circular rings. If we say the radius of central bright ring is r, if the radius of central bright ring is equal to small r, and the focal length of objective of telescope, focal length of objective is equal to small f. As we say, small f is the focal length. Therefore, d theta, that is the resolving limit of resolution d theta. Look at that figure, that angle also d theta. So, d theta is equal to, here r be the radius, so arc by radius, d theta is equal to arc by radius. Arc is equal to r, radius is equal to focal length f, d theta is equal to r by f. Therefore, r by f is equal to, the value of d theta is put here, 1.22 lambda divided by d, or r is equal to 1.22 lambda f divided by d. So, the radius of that of central bright depends upon the wavelength of that of source of light and focal length of that of objective of telescope and diameter of the objective of telescope. So, more the diameter of the objective of telescope, more the resolving power of that of given telescope. That is the expression for resolving power of telescope. So, with the help of this video lecture, we understand resolving power of telescope on the basis of three technical terms mostly used. One is limit of resolution, resolving power of telescope, and Rayleigh's criterion. Objective of telescope having diameter capital D, two objects O and O dash which is placed at infinity. Due to that, Fraunhofer type of diffraction is observed on that of screen. The screen is placed at the focal plane of that of objective. Next, we calculate path difference in between these two. According to the condition for first minimum, the path difference is equal to lambda, so that satisfy the Rayleigh's criterion. Therefore, the limit of resolution is calculated. Actually, experimentally we show which is just increased the factor 1.22, and the resolving power reciprocal of the limit of resolution, that with the condition to get high resolution means the diameter of that of objective of telescope must be increased to having greater resolution. Next, the radius of central bright can be calculated. So, with this useful and informative notes, let me wind up this session. Thank you.